Alright, I'm going to start this before the other one finishes exporting, so I'm going to have a pop-up at some point. But okay, so remember before on hypothesis tests, or, well, anything, where we're using the t-chart, the degrees of freedom was sample size minus 1. ChiSquared has a similar situation where it's based on the categories, minus 1. There are two types of ChiSquared test. One is a goodness of fit, which checks, does your sample in any way not fit with the expected population? ChiSquared is always based on expectation. So if we start with, ChiSquared test, the null hypothesis is always it's independent or that it is like the population. Okay, it's always, yeah, there's nothing weird about this. Similar with a two-sample test, the null hypothesis is always they're the same. Okay. So in this case, this one's looking at a pair of dice, or one die, which is being rolled repeatedly. And the null hypothesis, mine are weird. These arrows mean subscript, and then when it points up, it means superscript. So anyway, this says what we expect to happen is that the probability of each side of the die is 1/6. And the null hypothesis is the die is weighted, that something's wrong with it. One of them doesn't have a 1/6. If one doesn't have a 1/6, then another one at least has to not have a 1/6. But anyway, so that was an example. In this case, this example, we are comparing now not to some evenly distributed thing, but to the way things were in 2000. In 2000, 19% were in the Northeast, and 22.9% were in the Midwest, and so on. And this economist wants to know if it has changed. So, our expectations for each of those is based on those percentages. So if we select 1,500 households, we expect 19% of them to be in the Northeast. So 19% of 1,500 is 285 households that we would expect to be in the Northeast. 22.9% we expect to be in the Midwest. So 22.9% of 1,500 is 343.5. In the South, 35.6%. So this is where we get our expected values. Then we compare our expected counts and our observed counts. So here's what we just calculated based on we're seeing if it's the same as 2000. And these are what he actually counted up when he went and checked the households. He's chosen a significance level of 0.05. 0.05, alpha is, okay, let me back up slightly. A type 1 error is when you reject the null hypothesis, but you should not have. So what that means is you had a pretty weird sample and you used a pretty weird sample to argue that the null hypothesis was false, but really it was just because your sample was weird. Alpha is the probability of that happening that you're okay with. So if you go into a test saying alpha is 0.05, then you're saying I'm okay with up to a 5% chance that I reject the null when I shouldn't have, that I get a freaky sample and prove, in quotes, that the null hypothesis is false and that I'm wrong. P, the p-value that you get back when you do the calculation, is the actual probability that you commit a type 1 error. Alpha is the percentage, the probability you were comfortable with of committing that error. P-value is the probability after having done your test that you actually did. Because you could say, oh, I'm 0.05, I'm okay with 0.05, but then you run the test and you get 0.002, and then really the probability of a type 1 error is super small. It's just 0.002. Okay, so we're allowing 0.05. Here are our observed counts and our expected counts. This should say chi sub 0 squared equals the sum of this is now the top of a fraction. There's a lot missing here. This looks crazy. I think it looks right for you. But anyway, what you do is for each one of these, you subtract observed minus expected, and then you square it. And then you divide by the expected value, because if you take, for an example, if you were doing a chi-square test between all the juniors in Plano ISD, so you have a bunch from West, a bunch from East, a bunch from Senior, and then not a bunch from here. If your expected count for people who were wearing blue, if that was for here, say 70 people, and at West for 300 people, then you're going to be more off as far as total people goes at West, because if you're 30 off of the 200 and something, it doesn't feel like a big deal, but if you're 30 off of 70, that's a huge deal. So we want to kind of weight them. The reason that we square them is because they'd cancel each other out. For every extra person in the South, we have lost people in the Midwest or the Northeast, right? Because it's a trade off. So if we just subtracted them, they would equal 0, because you'd be adding and subtracting the exact same amounts. Let me pause this and deal with it. Okay, so for every box in a chi-square test, you have an observed and you have an expected. And each time you subtract, if there's a difference between them, we're looking at how big is your chi-square. Is your chi-square big enough to say that these things were not as expected? So when we take them, we find how big are they, we square them, and then we add them up. And every time you have an observed value and an expected value that are different, you add something positive. The only way that you don't add from a box is if they were equal there. The observed and the expected counts were exactly the same, then that box doesn't add anything because it doesn't show anything is different. Okay, so if you take 269 minus 285 and you square it and you divide it by 285. 327 minus 343.5, you square that, so divide by 343.5. 554 minus 534, you square it, you divide by 534. 350 minus 337.5, you square it, you divide by 337.5, and then you add those all up. When you add these all up, you get 2.903. So 2.903 is your chi-squared value, which you then take to the table. So here's the chi-squared table. You have degrees of freedom here, and then you have the tails up there. So it's like a T table. But the way you find the degrees of freedom now, on a goodness of fit test, you don't take the number of households, you take the number of categories and subtract 1. So we have 1, 2, 3, 4 categories. We subtract 1, and then our degrees of freedom are 3. So 0.05 and 3, 7.815 is the critical value after which it's less than 0.05. So if you go 7.815 right here, that means this area over here is that 0.05 that you were willing to kind of risk. Your value is way over here though. You are not over in that region. The rejection region is this tail. The rejection region is always tails. You are not in that tail, so you don't reject. Okay, so this you would do similarly. These directions are for a TI-84, which is not what you have. And you have a Inspire, which is a little different. But if we take this, Okay, so I'm going to kind of calculate the chi-squared value without doing too much work here. So this one is going to be A minus 71.15 squared. Okay. So this is just take this value, subtract, I think 71.14 is the expected 500 over 7. I think it may be 71.4. Okay, so here's all these, and then I'm just going to do calculations, one variable stats from B, yeah. Okay, so the sum of the x's was 19.576. So 19.576 is our chi-squared value. And then we would compare it to the table. Okay, so chi-square value, and we have 7 values, so our degrees of freedom are 6. And then we wanted alpha 0.01. 0.01. So here we are, 16.812. So this is what we're looking at here is the right tail test. 16.182 is the one that has the rejection region to its right. Our value is 19.576, so we're on this side and we are in the rejection region. We reject the null and we determine that, in fact, it is not the same frequency on these different days. It probably would have been if you'd done this many years ago, but nowadays most births are induced and they're scheduled for a convenient day for the doctor, and so they don't do them on weekends quite as much as when it's just left to its own devices. It's spread out pretty evenly. Okay, so the test of independence is the one you've done before, and it uses this same table, but where our degrees of freedom on the goodness of fit, you only have one variable, and so the number of categories is the number of categories, and you just subtract 1. In a chi-square test of independence, you have stuff on either side. So in the case of this marital status versus happiness thing, you've got 1, 2, 3, 4 options on the top and 3 on the side. So what you do is, the way you would do area of it would be how many of these times how many of these. Similarly, you do how many of these minus 1 times how many of these minus 1. So you subtract 1 from both dimensions and then multiply them together. So when you've got your chi-squared, this is where Dr. Mann is kind of proven to you guys the same thing that I already proved to you last semester about why it's row total times column total divided by table total. But once you have your chi-square, so here it's, lordy, very, very big, 224.116. So you have degrees of freedom 3 times 2, degrees of freedom 6 again, alpha equal 0.05, so 12.592. 224.116 wouldn't even be in this picture, right? It's like way off my screen there. Definitely in the rejection region. I've shown you guys, I think, how to run this test on, this is again on an 84, and we've got inspires. So let me go back, get these numbers for you, and do it on here. Okay, so we go to, let's close that. I want to do scratch. So I want to create a matrix, so I go to Menu, Matrix and Vector, Create, Matrix. I've got 4 columns and 3 rows. You just put in the observed values, it can calculate the expected values from that. And then you have to store it and name it. Okay, so now this is A. Now I go statistics, tests, chi-squared two-way test, that's a test of independence. I'm going to choose A. And here's that chi-squared that we just calculated, the 224.116. All we're able to do with the chart is look and see, is my p-value less than a given alpha, because it just has the boundaries for each alpha on the table. Right, these are all the boundaries. If this is the alpha you want, then these are your boundaries based on your degrees of freedom. It does not tell you, if you have 224.116, what's your actual p-value. This one does. So if you do it in the calculator, you know that there's a 0.00044 zeros 137,887 chance of this sample being like this if these two things are independent. Okay, and the other thing about chi-square is you need these to not be less than 5. You're allowed like 20% to be less than 5, but it's really better if none of your expected values are 5. So if you want to have this many categories, this is 12 categories, if you only ask 40 people, you can't run a chi-square with these categories because you don't have enough people to have 5 as an expected value in each box. So you would have to just split it between happy and not happy and either married or not. Like, you wouldn't be able to have this many categories if you couldn't ask more people. So these are boundaries, and on the T, the Z, these are boundaries also. Okay, so that is that. Okay, so if we wanted to do this one now, I wish I knew how to clear a scratch pad. There it is. Excellent. Okay, so first I want to add a matrix, and I've got 2 rows, 3 columns. 51, 5, 16, 15, 32, 152, 163, store. Now that's going to be A, stats. And this time the p-value is 0.0006. The chi-square is 14.7. Chi-square of 14.7 means it's bigger than the boundary. I know that because this is less than 0.05. We want a 0.01 level actually. 3 by 2, so 2 times 1. So our degrees of freedom are 2, and we want 0.01. 6.965 is the cutoff. 14.7 is bigger than 6.965, so 0.00641 is less than 0.05. But again, we don't really have to know the p-value unless someone asks us, what's the probability that you committed a type 1 error, and then we need to know p-value. But since whoever told us to run this test was okay with up to 0.01, all they really need to know is the probability that error is less than 0.01, usually. Okay? Trying to think of what, if anything, I'm missing here. I guess I'll go on to the next one. That's not what I want. That is also not what I want. Guys, I'm so tired. This is like nuts. Camtasia is what I want.